Hello, today we're going to be talking about elemental composition of pure substances. Taking a look here at 1.3, the College Board AP Chem curriculum. And day 2 we'll be looking at 1.4, composition of mixtures. So the enduring understanding, of course, is that chemical formulas identify substances by their unique combination of atoms. So we're going to be looking at the combination of atoms, their subscripts, and their formulas based off of experimental data. So by the end of the 1.3 example problems, you should be able to, the learning targets, I can calculate the percent composition of elements in a compound by mass, and also determine empirical formulas, molecular formulas in a compound by given data. Now the data is going to look different in different problems, and we're going to show you how different ways they can represent that. So let's review percent composition. The law of definite proportions. Okay, the law of definite proportions tells us basically that we can calculate percent composition. States that a given chemical compound always contains the same elements in the same exact proportions by mass. So let's think about this. An example of carbon dioxide. Carbon dioxide has 27.29% carbon by mass and 72.71% of oxygen by mass in its compound. Now, how would you calculate this? You would calculate this by using the masses off the periodic table, like carbon right here, 12.01, and oxygen is 16, but there's 2 of them in the compound here, so we would multiply that by 2 to get 32. Now this U here, all that's representing is atomic mass units. It's actually called unified atomic mass units, which is signifying that it's based off the measurement of carbon-12. So whenever you see a U here next to it, you're referring to atomic mass units. Now, once you get the individual masses of the elements in the compound, you must find the total. So you find the total here, and you end up getting the total is 44.01. Now we can calculate the percent of each of the elements in the compound. So for carbon over here, we're going to do 12.01 divided by the 44.01 times 100, and that's where that 27.29% comes from. Basically, this is following regular percent problem. The part over the whole times 100 is going to give you the percent. Now our part is the mass of the element over the whole, which is the total mass of the compound, times 100 gives you that percent. Over here for oxygen, 32 is the mass of the 2 oxygens divided by the total, which is 44.01 times 100, and that's where that percent came from. Now, empirical and molecular formulas. Hopefully this is a review of last year. Empirical formulas are compounds in their simplest ratio of the subscripts. So it's a compound that shows that simplest ratio. Now the chemical or molecular formulas, and we use chemical here because sometimes they're not actually molecules, but for the most part you're going to see these as organic molecules where there's carbon, hydrogen, oxygen, nitrogen, and other nonmetals in it. But occasionally they'll have one that could be an ionic compound or something like that. Compound that represents the actual number of atoms in each element in that compound. So these ones don't necessarily, or they're not going to be reduced, although sometimes the empirical formula is actually also the molecular formula. And some empirical formulas are actual compounds and they have their own names, and then some empirical formulas just don't exist in nature because that's not how the atoms would bond together. You need more atoms in order to make it work, so the molecular formula would be the only one that would be in existence. So example, determining empirical formulas, looking at chemical formulas over here like tetraphosphorus decoxide, and this one right here in the middle is trisulfur hexafluoride, and then this one over here is just sucrose, which is table sugar, stuff that you put in your coffee or in your, you bake with it, that kind of sugar. So in order to determine the empirical formula here, you have to look for a common factor in the subscripts. So this is 4 and 10, the common factor is 2. So we can divide both of them by 2 and therefore reduce it down to P2O5. Looking here at this example, we have a 3 and a 6, so the common factor is a 3. We would divide by 3, so we would get SF2. Now sucrose over here, C12H22O11, looking at those subscripts, they're not reducible. So in this case, the empirical formula is actually the same as the molecular formula, which would be non-reducible there. Now, this is the first way they're going to represent the data, example 2 here. They're giving you percents of each element. So nitroglycerin contains 15.87% carbon, 2.16% hydrogen, 18.15% nitrogen, 63.41% oxygen. And they want you to find the empirical formula. So when we're just doing the percent problems, we like to follow this easy rhyme to help us remember the steps. And in other problems, you can still use parts of the rhyme depending on what type of data they give you to begin with. But the first step, of course, is changing the percent to the mass, percent to mass. So we're assuming a 100-gram sample, change the percent sign to grams. Just cross it out and change it to grams. Second step would be to change the mass to moles. So percent to mass, mass to mole. Basically use a t-chart or convert it over by dividing by the molar mass. The third step is divide by small. And when we're talking about small here, we're talking about the smallest mole value out of every one. Divide by the all the mole values by the smallest mole. And last but not least, sometimes you have to implement this steps, not always, but multiply till whole. So if you do end up getting one that is not a whole number when you do the divide by small, say you get something that's a 0.5 or something that's like a 0.33, something that's around a 0.66. Even I've seen 2 5s and 0.2s as well. And usually there might be like a 0.65 or a 0.34, something very close to that, but you would know that you need to multiply it until you get the whole number. So in order to make 0.5s turn into whole numbers, you have to multiply through by a 2, and every element gets multiplied by that 2 if you have a 0.5. The 3, 3 and the 6, 6 is an easy one because all you have to do is multiply them all by 3. So multiply through by 3 and you'll end up getting a whole number. If one of the elements ends up in that particular arrangement, all of the elements would be multiplied by 3, and then 0.25 you could probably see is a times 4. 0.2 would be multiplied by a times 5. Once you do that, the whole numbers, okay, they eventually turn into, then you write out the formula, and those are your subscripts when you do these 4 steps. So percent to mass, mass to mole, divide by small, multiply till whole. You get those whole numbers become the subscripts in your empirical formula. Now, to complete this problem, I like to set it up as a nice little table, and I just follow the elements in order. Excuse me, let me fix that. I like to follow it in order of the elements, so I'm going to put carbon over here. The 15.87 grams is the carbon, and then I'm going to get ready to change that to moles. The next one is hydrogen, which is the 2.16 grams, changing that to moles. Then comes the hydrogen, then of course is the nitrogen after the hydrogen. That's going to be 18.15 grams. And last but not least is the oxygen, which is 63.41 grams. Now here we're changing them all to moles, so we divide them by their molar mass. Carbon is 12.01 on the periodic table. That equals 1 mole of carbon. Hydrogen is 1.01 grams off the periodic table. That equals 1 mole hydrogen. Nitrogen is 14.01 grams. That equals 1 mole of nitrogen, and oxygen is 16 grams. And that equals 1 mole of oxygen. Then we have to calculate these using the significant figures here. So this one would have 4, hydrogen would have 3, nitrogen has 4, and so does oxygen. So use your calculator and be able to calculate those moles. All right, so looking here after using my calculator, it appears that the carbon is 1.321 moles. The hydrogen is appearing to be 2.14 moles of H. The nitrogen, 1.296 moles of N. And last but not least, oxygen is 3.963 moles of O. Now I need to look for, out of these 4 moles, which one ends up being the smallest. So if I look here, I see the nitrogen is the smallest amount out of all of those. So I'm going to divide every single one of these by the nitrogen mole amount. Okay, so this one obviously, when you divide it, is going to be a whole number of 1. So we divide these out all by the 1.296. Don't really need the N though, they just divide by the smallest mole. And then divide this by 1.296. And then you calculate those to get your possible whole numbers, although you might have to multiply till whole. Okay, so when you divide this out, you end up getting 1.02, which is virtually a 1. You divide this one out, you get 1.65. You divide this one out, the oxygen here, and you get 3.06, which is really equivalent to a 3. Now looking at here, 1, 1.65, 1, and 3. We do have the issue here where this one did not come out to be a whole number. So we'll need to multiply everything through. 0.65 is close to the 66. So really, to get a whole number from that, we would multiply everything by 3 to see here what we would get. So this would be 3 for the carbon, 3 for the nitrogen, and 9 for the oxygen. And the hydrogen ends up being like 4.95, which is really a 5. Look here, we have 3 carbons, 5 hydrogens, 3 nitrogens, and 9 oxygens. So it'd be C3H5N3O9 for nitroglycerin. This would be our empirical formula. Now, example 3, they didn't give us percents to start with, so this is a different option. Instead, they give us grams of oxygen and grams of iron. So basically, we get to skip the first step of the percent to mass. We can go directly from mass to moles. Okay, so I just set it up again using iron here, 11.66 grams. Changing that to moles. If you look at your, here, let me fix that line. It's a little skewed. Straighten it a little bit better. Okay, so this is grams of iron. So that's going to be 55.85 grams of iron equals 1 mole of iron on the periodic table. And then we do our oxygen, which is 5.01 grams of O, and that's 16 grams. O equals 1 mole of O on the periodic table. Time to calculate the moles. So looking here, the mass of the moles of the iron is going to be 0.2088 moles, following sig fig since they have 4 over here to start with. Then we get 0.313 moles of our oxygen. Now looking out of these two, this one's obviously the smaller amount, so we're going to divide both of them by this number. Of course, that gives you 1. We divide this one by the 0.2088, we end up getting around 1.5. So here, once again, it's not a whole number. So we have to multiply everything through to get a whole number for oxygen. Times 2 here, times 2, what you do to one, you have to do the other. So this is going to be 2. This is going to be a 3. That means 3 to 2 here ratio, it's going to be Fe2O3. So that ends up being iron 3 oxide. Now we're going to talk some combustion analysis and what we can remember about combustion reactions in general. Combustion reactions have to do with, mainly what we're going to be looking at is organic combustion. So we had some kind of organic compound. One of the reactants is always oxygen. Then one of the products is carbon dioxide. The other product is typically water, and sometimes you can have other things depending upon what is in this organic compound to start with. Regular hydrocarbons are just C and H's, but a lot of times you're going to see ones that have nitrogen, chlorine, sulfur, other nonmetals in those organic compounds. But oxygen's always one of the reactants. Carbon dioxide and water are definite products. Sometimes in incomplete combustion, you'll end up with some carbon monoxide as well. And then if it has nitrogen, sulfur, chlorine, those compounds will come over here, and you'll have ones that have like nitrogen oxides or sulfur oxides, like SO2, SO3, a lot of those. You can get like Cl2O, a bunch of different compounds. We don't really have to pay too much attention to that because based off of the data, we'll be able to figure out the components. Now, talked about this in general, the reaction of hydrocarbons or organic molecules with oxygen. That's one of the reactants here, noted in the equation down here. Products are always carbon dioxide and water. Okay, those are the usual ones that you see. Occasionally there's other products with other elements. That depends on, like, yes, if you have like a hydrocarbon that has, you know, chlorine in it or has sulfur in it, something like that, that has nitrogen in it, like I said before, you'll see the like nitrogen oxides over here, possibility of different ones. Now, like I said, not necessary to know in the balanced reaction because we will be using the law of conservation of mass to help solve these problems. So really it's about the mass of what you start with is equivalent to the mass of what you end with. So the mass of an element in the reactants is equal to the amount of that same element in the products. And that's really how we're approaching this. We're not approaching it from a stoichiometry perspective. It's about the masses in the reactants and then the products. So example 4 is showing you a combustion analysis where we have carbon, hydrogen, nitrogen, and oxygen. They've been analyzed. They've used a 1.2359 gram sample, burned it in excess oxygen, and found to have 2.241 grams of carbon dioxide. The combustion analysis also showed that the sample contained 0.0648 grams of hydrogen. So that information will be important later. Now this is an actual AP kind of question that was on a previous exam, and this would be kind of like part A, even though I listed it as 1. And it kind of goes in sequence, and you'll see how that you build one off of the other in order to get to the ultimate end of the answer. And like part A, part B, part C, part D, which would be 1, 2, 3, or 4, those are all worth 1 point of the free response question. So we want to determine the mass of carbon in this gram sample. Now, if we look at our reaction here, we have a carbon, hydrogen, nitrogen, that's supposed to be a Z, by the way, and an oxygen compound to begin with. We don't know what the subscripts are. That's what we're trying to find. It's reacted with oxygen. It's going to give us carbon dioxide and water, even though they didn't tell us about water, and some other nitrogen compound. They did tell us about the carbon dioxide, though. They told us 2.241 grams of carbon dioxide were produced. So we can use the grams in the carbon dioxide that are actually carbon to figure out the grams of the carbon that are actually in our sample that we started with. It's a simple conversion. So we start with 2.241 grams of CO2, and we have to work it all the way to the grams of the carbon. So 44.01 grams of CO2 equals 1 mole of CO2. Now this is the step where you have to split up the carbon dioxide into its moles of carbon and moles of oxygen, although we're only really looking at the carbon at this point. So 1 mole of CO2 has 1 mole of carbon because there's only 1 atom of carbon in the entire molecule. Then we can do 1 mole of carbon is equivalent to 12.01 grams of carbon. And this is going to end up giving us our grams of carbon that's in the CO2, but because of the law of conservation of mass, that means it's also going to be the grams of carbon that's in this original compound. So they will cancel nicely. We have the carbon dioxide grams canceling the moles of carbon dioxide canceling, the moles of carbon canceling, and then we end up with our grams of carbon. And when you multiply the 2.241 times the 12.01, you divide it by the 44.01, you end up getting 0.6116 grams of carbon. Now that's because we started with 4 significant figures over here. We would want to end with 4 significant figures over here. All right, so that's the first part. Step 1, finding the grams of the carbon. So that one's done. We found the grams of the carbon. Now, when the compound is analyzed for nitrogen content only, the mass percent is found to be 28.84%. Determine the mass in grams of the nitrogen in the compound. Now, this is basically just part over whole times 100 gives you the percent. We know the percent is 28.84. We don't know the part of the nitrogen. What we do know is the whole sample here. How many grams were in that sample? 1.2359, and then times the 100. You don't really have to set it up this way. Most people automatically know to change their percent to a decimal and then multiply it by the total, the whole, in order to get the part. So I would just probably lay it out like that, changing that to the decimal form of the percent, multiply it by the gram amount in the total sample, and then you end up getting your final answer for the nitrogen. So this one ends up being 0.3564 grams of our nitrogen. So that means we've also found our grams of our nitrogen. Check and check. The one thing also we all were told in the problem is our grams of hydrogen in that original sample. So we actually have this part too. So that's out of the way. The last thing to find in order to do the empirical formula has got to be the oxygen. And yes, it says determine the mass in grams of the oxygen in the original sample. Now this is nice because it becomes just a subtraction problem. We take our original 1.2359 grams, the entire compound, we subtract out the carbon, we subtract out our hydrogen, we subtract out the nitrogen, and that's going to give us the grams of our oxygen. So the grams of oxygen, subtract that out, you get 0.2031 for our grams of our oxygen. And now that we know all of the grams, we can go to calculating the moles, divide by the small, multiply till whole to finish out the empirical formula, which happens to be the next step, determine the empirical formula of the compound. So I listed it here so I can have it set up as a table, and we can go ahead and crank that out where we change the grams of carbon over. 12.01 grams carbon equals 1 mole of carbon. Change out the nitrogen here. 14.01 grams of nitrogen equals 1 mole of nitrogen. The mass of oxygen, divide by 16 grams here, equals 1 mole of oxygen. And last but not least, our hydrogen here. 1.01 grams of hydrogen equals 1 mole of hydrogen. Calculate all those out, and then we'll decide on which one will be the smallest and what we need to divide by. So for the carbon, we get 0.05092 moles of carbon. For the nitrogen, it ends up being 0.02544 moles of nitrogen. For the oxygen, it ends up being 0.01269 moles of oxygen, and for the hydrogen is 0.0642 moles of hydrogen. Looking at these numbers, this is 0.5, 0.2, 0.1, 0.6, so this one's going to be the smallest. We're going to divide all of them by the oxygen moles. So divide them all by the 0.01269. All of them get divided by that, and we end up with our numbers. So let's go ahead. This one obviously is going to be a 1, so let's go ahead and divide them all. Okay, so this one is approximately 4.01, which is really a 4. Nitrogen ended up being like a 2, almost on the nose, and then hydrogen was 5.05, which is really a 5. So now that we know our elements and their whole numbers, this one we didn't have to multiply till whole on. So that ends up working out nicely. Now, the order that they presented it in the problem was carbon, then hydrogen, then nitrogen, then oxygen. So we're going to write it in that order. So it's going to be C4H5 N2O. That's our empirical formula for this particular compound. For example 5, combustion analysis. This one's a little bit more tricky than previous one because you have to think about it in 2 separate steps. The first one here, an organic compound was found to contain carbon, hydrogen, and chlorine. When a 1.5 gram sample was completely combusted in air, 3.52 grams of carbon dioxide was formed. So that's easy. That's very similar to what we did in the first step of the last problem. We're going to, use the carbon dioxide to find the carbon. In a separate experiment, the chlorine, in a separate experiment, the chlorine in a 1 gram sample of this compound was converted to 1.27 grams of silver chloride. Determine the empirical formula of the compound. So, can start with the first part, which is pretty simple, where we're just finding the carbon from the carbon dioxide here. So we'll start with the 3.52 grams of CO2, and we're just going to change this part over into the grams of carbon and knock that one out and get the carbon amount decided. So 44.01 grams CO2, 1 mole CO2, in 1 mole of CO2 there is 1 mole carbon, and then 1 mole of carbon is 12.01 grams of carbon. So we'll go ahead and take a moment to calculate that. And end up getting, for the carbon, 0.961 grams of carbon. 3 significant figures over here, so that's why I'm going with 3 significant figures there. So this part's been taken care of. Check, we've got the carbon. Now, the second part is helping me to find chlorine. So Once I get the chlorine, I can subtract out the carbon and the chlorine to find hydrogen. However, this is taking place in a separate reaction. And what you should do is try to kind of get an idea of what that reaction, a separate experiment, is going to look like here, the second experiment. So basically, we had our original compound, which was like CXHYClZ. Okay, this was our original compound. The first one, it was combusted with oxygen. So we had that first reaction take place where it was combusted with oxygen. It produced the carbon dioxide, the water, and whatever chlorine compound it got. Okay, so this was that 1.5 gram sample. And we figured out the carbon based off of the CO2 here, the 3.52 grams. So that's where we got this amount, okay? Now we have to consider the second experiment where they took this same compound, they just took a different sample size of it, which was 1.00 grams of it. They reacted it with some kind of silver compound. We don't know what it is. It could be silver nitrate, could be something else. So not really sure what that is, but they reacted it with something that had silver in it so that it would produce silver chloride and then, the other products as well. We do know that 1.27 grams of the silver chloride was formed. Now, what you have to consider here is to find chlorine. Remember, the amount of chlorine in the reactants is equivalent to the amount of chlorine in the products following the law of conservation of mass. So using our compound here and our knowledge of the law of definite proportions, where we know that we can calculate the percents of each in this compound, we can figure out the amount of grams that was in the silver chloride here. So first things first, though, is I'm going to go over here and do the percent composition of silver chloride. Silver is 107.87 grams, or atomic mass units. Chlorine is 35.45 atomic mass units, so this is 143.32. Now, we just want the chlorine amount, so we do the 35.45 divided by the total times 100, and this is going to give us, you calculate that out in your calculator, and you should get 24.7%, that is Cl. So one thing you might have noticed is I did write this backwards. I said 45 here, but yeah, I wrote 54, so let me correct that, because chlorine is 35.45, not 54. That's me transposing numbers by accident and calculating that. We still end up getting 24.7 because I calculated it correctly, just transpose those numbers there. All right, now I know the percentage of chlorine. This is, chlorine is 24.7% of the silver chloride compound. So now that I know that the 24.7 of the 1.27 grams, I can figure out the amount of grams in this particular reaction. So I do 1.27 times 0.247, and that is going to give me 0.314 grams Cl. Now, this is in this particular reaction, we're still here in this reaction, so that means out of this 1 gram sample, we have 0.314 grams. That's out of this sample though, okay, out of the original compound, which also has its percents of each element in it. So if I'm looking correctly at this, I can figure out the percent of the chlorine by mass in this particular unknown compound. So I do that, and I do 0.314 divided by the 1 times 100, which is going to give me 31.4% chlorine in this unknown compound. That is helpful to me for later, because now to find the chlorine over here in this particular original compound, I can take the percent of that. So if the original compound here, the 1.50 grams, and I multiply that by the 0.314%, which is, the 31.4% is 0.314 in decimal, I know how much of the 1.5 grams is my chlorine, which ends up being 0.471 grams chlorine. Now that I know these two values, I can easily find my hydrogen, which I need. All right, so let's go ahead and subtract that out. Our original compound amount, the 1.50 grams. Subtract out our carbon here, 0.961 grams. That was the carbon. Subtract out your chlorine. And that's going to give us our grams of our hydrogen. So go ahead and take a moment to subtract that. We end up getting 0.068 grams of our hydrogen. Now that we have the grams of all the components, the carbon, the chlorine, and the hydrogen, we can do the mass to moles, divide by small, multiply to a whole part of this problem. So let's go ahead and set this up. Put our carbon here, the hydrogen is next, and the chlorine here. And we just go ahead and continue on doing the basics of changing it to moles. The hydrogen's next, following the order that they gave it to me in the problem. This is 1.01 grams of hydrogen, that equals 1 mole of hydrogen, and our chlorine 0.471 grams. Chlorine on the periodic table is 35.45 grams, equals 1 mole of chlorine. I guess I should put the carbon, the hydrogen, and the chlorine in there as well. So calculate all of those, and then we'll decide which one is the smallest mole. Okay, so the carbon looks like it's 0.0800 moles. The hydrogen, 0.067 moles of hydrogen, and 0.0133 moles of chlorine. And looking here, it appears that the chlorine amount is the smallest, so that's the one we're going to divide by. Okay, so we divide everything by the 0.0133, divide them all here, and this one's obviously going to be a 1. The 0.067, that one looks like it's an approximate 5. It's like 5.04, and the 0.08 divided by 0.0133, that's 60.01, so that's an approximate 6. So we end up getting C6H5Cl as our empirical formula. Now obviously, see, this one's a little bit more challenging, it takes more steps. You have to really work with those percents using the law of definite proportions as well as the law of conservation of mass and working it backwards. So take a moment to try to process all of those steps.